Carnot cycle, Carnot theorem, and then corollary of Carnot theorem. So whatever the heat engine you take, reversible heat engine is the one which gives the highest efficiency. Okay. Today I'll start another important chapter in module 3, that is entropy. Okay. The screen is visible, guys. Is it visible? Screen is visible. Can anyone tell me?
Yes, sir.
Okay. Okay, today I'm discussing the new chapter, that is entropy in module 3. Okay. Uh, so here, first I'll discuss the syllabus part. You see the bottom portion, entropy. We're going to study Clausius inequality, statement, entropy definition, property, change in property, entropy as a quantitative test for reversibility, principle of entropy, and entropy as a coordinate. These are the things related to entropy. Okay. Please, guys, I'll share another PPT, not this one. Okay. Okay, a slide is visible. Okay, there is some problem in internet connection. Okay. Is it visible?
Yes, sir.
Okay, I'll start the session now. Okay. Okay, we discussed the work interaction in first module, that is first law of thermodynamics. You are all aware that the work done is given by P into dV, that is product of P into dVs, and we used the same relation for deriving the work done for various processes like constant volume, constant temperature, next isothermal, adiabatic and polytropic process. In second law of thermodynamics, we are going to deal with another important concept called as the entropy. Okay, first law of thermodynamics gives rise to a concept called as internal energy. Like that, second law of thermodynamics gives a new definition called as entropy. Okay, how the internal energy is associated with first law of thermodynamics, like that, entropy uh, related with second law of thermodynamics. Okay, entropy, it is basically a thermodynamic property. You remember, like the properties we studied in module 1, that is thermodynamic properties like pressure, volume, and temperature, like that. Entropy is also a thermodynamic property, and it is mainly related with the heat and temperature. You remember, okay? It's mainly related with the heat and temperature because second law of thermodynamics mainly deal with the heat and its interaction, forward direction and backward direction, like that. So entropy is a thermodynamic property which is mainly related with the heat and the temperature. As you are going to add the heat to the system, the entropy of the system increases. And whenever you are going to remove the heat from the system, then the entropy of the system decreases. Okay, so actually we don't have proper definition for entropy, just you have going to write it as it is a thermodynamic property of the system mainly related with the heat and temperature. Okay, and it is mainly function of quantity of heat, which shows the possibility of conversion of heat into work. How much conversion of the heat into work is possible, that we are going to study using entropy concept. Okay, so in first chapter you studied PV diagram. Okay, the nature of PV diagram for various process like constant volume, constant temperature, and we are having another diagram called as TS diagram in this chapter. Okay, so you observe the diagram properly. Okay, in PV diagram, y coordinate is P and x coordinate is x, like that in TS diagram. So we are having another diagram called as TS diagram, mainly related to heat transfer. Okay, so work done is represented with PV diagram and heat transfer is represented with TS diagrams. Always you have to take T as y coordinate, and S is called as entropy as the x coordinate. Okay, let us consider a working substance. You see the uh, a TS diagram. Okay, it may be any process. Okay, I'll explain how we are going to write the TS diagram for various process. Just for getting the equation of entropy, just you consider any process. It takes the process from state 1 to state 2. Okay, and y coordinate is temperature and x coordinate is entropy. It's nothing but yes. Okay, and let dq be the amount of heat supplied to the working substance. Okay. As I said, this entropy is mainly let dq. Okay, let dq be the amount of heat supplied to the working substance in which the entropy of the system is increases. Okay, how we are having EW equals to P into dV, like that we are going to write the equation that is product of temperature and increase in the entropy. Ts is nothing but S2 minus S1. That is final entropy value. minus initial entropy value. It's very similar to our work transfer. In work transfer, we are taking dW to P into dV. Just we are going to T into ds in case of heat transfer. Okay, and here it is the product of T into ds. Okay, and you see, suppose I am taking one point, intermediate point between the process 1 to 2, and the amount of the entropy during that state is ds. Okay, it is represented by ds here. Okay, S1 is the entropy at initial state, and S2 is the entropy at final state, and ds is the entropy during some interval, okay, at some intermediate state point. Okay, that is dependent by ds. So dq is the amount of the heat transfer in that particular state. It is the product of temperature. Temperature is the temperature at that particular point, and ds is the value of entropy at that particular point. Okay, you remember this dq is we are going to take at a particular state. Okay, in order to get the total heat transfer during the state 1 and 2, what you are going to do? You are going to integrate this equation between the limits 1 to 2. Okay, so dq is the amount of the heat supplied to the working substance at a particular state. T is the temperature at that particular point, and ds is the entropy at that particular state. In order to get the total heat transfer during the process 1 to 2, we are going to integrate the equation 1 between the limits 1 to 2. You see, whatever equation we are having, we are going to integrate that equation between the limits 1 to 2. Integration of dq between the state points 1 and 2 equals to integration of t into ds between the state point 1 and 2. Okay, so dq equals to tds, but our aim is to find out ds. How we are going to write ds? Ds is nothing but dq by t. Okay, so the equation is dq equals to t into ds, or we can write in this format: ds equals to dq by t. Now you can integrate, either write this equation or you can write this equation. Integration of ds equals to integration of dq divided by t. So integration of ds is nothing but s2 minus s1. As we discussed point function and path function in the previous model, point functions are the thermodynamic property, okay, with their the definite integrals. On the other hand, the work transfer and heat transfer are uh, the indefinite integral. Okay, we are not going to integrate, we are not going to differentiate those properties, that is path function. On the other hand, the point functions are the definite integrals. Okay, so integration of ds equals to 2 minus s1 equals to integration of dq by t. Okay, you remember this equation for the entropy. Okay, entropy is a property of the system. Okay, it's mainly related to the heat transfer and temperature. As the heat added to the working substance of system, then the entropy of the system increases. That is, you are getting positive value. On the other hand, whenever you are going to remove the heat from the system, then the entropy of the system decreases, and the standard formula for entropy is given by ds equals to dq by t. You remember the standard formula, or dq equals to t into ds. Standard formula for entropy: ds equals to ratio of the heat transfer to temperature. Okay, it is mainly depends upon the two parameter. One is q and another one is temperature. Okay. Now I'm going to derive the expression for the change in entropy for various processes. Okay. How we derive the expression for work done during various process. Okay, in this chapter, we are going to find out the expression for entropy change during various thermodynamic process. Okay, let us consider mass of the gas as mkg, initial pressure as P1, volume as V1, temperature as T1, and initial entropy as S1. Okay, and the final state represented by E2, V2, T2, and S2 respectively. Okay, so you should know how to draw the TS diagram for the various process. Okay. Okay, before that, I'm going to derive the general the entropy relation. Okay, concentrate more on this entropy change equation. Most important, they'll ask these derivation for 10 marks. Okay, that's why try to understand each and every step properly. Okay, so already you know the law of conservation of energy, that is first law of thermodynamics, undergoing a change of state is given by Q equals to delta U plus W. Whenever you are going to write in the differential format, you can write uh, dq equals to du plus dw. Okay, so this is the uh, equation in differential form. General format is q equals to delta u plus w. Whenever you are writing in the differential form, you are going to write this form. Okay, that is dq or delta q. Okay, delta q equals to du plus delta w, where delta q is small change in heat and du is small change in internal energy. Better you write du only. Dq equals to du plus dw. Okay, so dq is small change in heat, du is the small change in internal energy, and dw is small change in work done. Okay, this is what we are taking from first law of thermodynamics. It is the differential form of first law of thermodynamics. dt, it is small change in temperature and dv is small change in volume. Okay, so that before deriving the derivation for entropy change, first we are going to write the first law of thermodynamics in differential form. Now, so dq equals to du. Okay, as I said in the previous class, whatever process it is, the du, that is internal energy, is a function of temperature only, and it is always given by mcv into dt. Remember, this is the standard formula for the internal energy. Whatever process it is, whether it is constant temperature, constant volume, whatever it is the standard formula for change in internal energy. So dq you write as it is. Du is mcv dt plus, okay, dw. Already we studied in first law of thermodynamics, that is dw is pdv. Okay, so just you replace du by mcv dt, and dw, that is work done, is given by p into dv. Okay, so now, okay, understood this one. Okay, first how we are going to write the standard equation of first law of thermodynamics. dq equals to du plus dw. Du is nothing but mcv and plus dw, third term is pdv. Okay, now we are going to divide throughout by the term t. Okay, dq by t, you are going to divide throughout the equation by t. So dq by t equals to mcv into dt by t plus pdv divided by t. Okay, just you divide throughout this equation by t. dq by t equals to mcv into dt by t plus p into dv by. And we know that, just we understood that the ds, the change in entropy, is the ratio of dq by t. So dq by t is nothing but ds. You remember, ds is always dq by t. So dq by t is ds, and from ideal gas equation we have pv equals to mrt. Okay, so you are going to study ideal gas equation and real gas equation in module 5. Okay, already you studied this ideal gas equation. pv equals to mrt, or we can write in this format: P by T equals to MR by V. Okay, so we are writing the ideal gas equation in this format: P by T equals to MR divided by V. Okay, they are having the same meaning. Okay. Now we are going to substitute the value of dq by t is nothing but ds. You put mcv dt by t as it is, and you are going to replace the third term, that is p dv divided by t, as P by T is nothing but MR. Okay, just you see the third term. P by T is nothing but MR by V. Just you write MR dV by V. Okay, so you replace the ratio of P by T as MR by V in the third term. Okay, so we are writing this equation as ds equals to mcv into dt by t plus this ratio P by T as mr into dv by v. Okay. Next step, you are going to integrate the both side. Okay, you understand this derivation properly because the same thing we are going to use in the numerical problems. Okay, so try to understand correctly. Okay, derivation, three derivation are there. Try to understand. So this is the standard equation to find out the entropy change or any process. Okay, then once you understand this equation, we are going to find out for individual process. These are the general equation. Okay. So ds equals to mcv into dt by t plus mr into dv by t. Okay. Next, we are going to integrate on both sides. Integration of ds equals to, okay, between the limits s1 to s2, two states, okay, two state point between the states s1 and s2 equals to mcv is the constant term, integration of dt by t between the limits t1 to t2 plus mr is the constant term you have to take outside, integration of dv by v between the limits v1 to v2. Just first you write the differential form of first law of thermodynamics, then you are going to divide throughout by t, and then you are going to replace the term. Okay, then you are going to integrate on both sides between the state points 1 and 2. Okay. So after simplification we get integration of ds between the limits s1 to s2 is s2 minus s1. Okay, that is, as I said, entropy is a thermodynamic property like other properties, pressure, volume and temperature. So mcv is constant term and integration of dt by t between the limits t1 to t2 is ln. Okay, it is natural logarithm t2 by t1 plus mr is a constant term and ln v2 by v1. So this is the entropy change equation for any process in terms of temperature and volume. You remember, so whatever we derived this equation, which is in terms of temperature and volume, it's the one equation. Okay. Next equation. Okay. As we know that, okay, P1 V1 divided by T1 equals to P2 V2 divided by T2 from ideal gas equation. That is P1 V1 divided by T1 equals to P2 V2 divided by T2 because we are taking between the two state points, and then you can write the equation as V2 by V1 equals to, you can write in this format P1 by P2 into P2 by T1. Okay. First you have to write ideal gas equation, then you have to take the ratio V2 by V1 equals to P1 by P2 into T2 by T1, or the ratio T2 by T1 is nothing but the P1 by P2 into V2 by V1. Okay, so in terms of volume ratio we are writing like this, and in terms of temperature ratio we are writing the ideal gas equation in this format. Okay, now we are having, you see, the third term V2 by V1. Okay, now we are going to substitute the value of V2 by V1 as P1 by P2 into T2 by T1 in this equation. Okay, whatever equation derived, this is the entropy change in terms of temperature and volume. We are going to replace V2 by V1 as P1 by P2 into T2 by T1 in this equation. How we are going to write? S2 minus S1. Okay, don't change the first term. Okay, only we are going to substitute the value of V2 by V1 as P1 by P2 into T2 by T1 in the third term. So S2 minus S1 equals to MCV into ln T2 by T1 plus MR into ln P1 by P2 into T2 by T1. This is the ratio of V2 by V1. Okay. Now, next term, MCV ln P2 by P1 plus MR ln P1 by P2. Just you simplify this equation. MR ln P1 by P2 plus MR ln P2 by T1. Okay. Now you are going to apply. You see what are the common terms are there. Okay. So here first term we are having the ratio T2 by T1, and in the third term also we are having the ratio T2 by T1. So you can write like this: M into CV plus R. Okay, you consider first term and third term. Okay, so M into CV plus R into Ln T2 by T1 plus MR Ln P1 by P2. So, as I said in the previous class, R is Cp minus Cv. You remember? So, gamma is Cp by Cv. One more formula is that R, general gas constant, is the difference of specific heats. R is always Cp minus Cv. So, we can write uh, Cv plus R is nothing but Cp. Okay, you remember R equals to Cp minus Cv, or Cp equals to Cv plus R. Okay, so certain values you should remember. One is the formula R is Cp minus Cv. Second formula gamma is Cp by Cv. The value of Cp is 1.005 kilojoules per kg Kelvin. The value of Cv equals to 0.718 kilojoules per kg Kelvin. Okay, R is Cp minus Cv. So we can write M into Cp ln T2 by T1 plus MR ln P1 by P2. So whatever equation you got, this is the expression for entropy change in terms of temperature and pressure. Okay, the first one is the entropy change in terms of temperature and volume. Second, what we derive now is the entropy change in terms of temperature and pressure. And one more is there, that is P and V. Okay, third one. Okay, now we derived two equations. One is in terms of temperature and volume. Second one in terms of temperature and pressure. And third one more expression is there. Okay, that is the entropy change in terms of pressure and volume. Okay. Now, okay, we got, you see that this equation, once again you take the ideal gas equation. From the ideal gas equation, we can write P1 V1 divided by T1 equals to P2 V2 divided by T2. So, equals to P1 by P1 equals to P2 by P2 into P2 by V1. Now we are going to substitute the value of T2 by T1 equals to P2 by P1 into V2 by V1 in equation here. Okay. See, first equation what we got, we are going to substitute the value of T2 by T1 as P1 by P2 into V2 by V1 in this equation. Whatever we derived first. Okay. Okay, substitute the value of P2 by T1 as P2 by P1 into V2 by V1. So S2 minus S1. Integration of ds between the limits S1 and S2 is S2 minus S1. Okay. Anyhow, I'll do how the entropy is a property like other thermodynamic properties. So we are going to discuss in the next class. So first you understand the derivation. MCV into ln P2 by P1 into V2 by V1 plus don't change the second term, that is MR ln V2 by V1. You put as it is. Next, you simplify this one. Okay. So MCV ln P2 by P1 plus MCV okay. So just to simplify, MCV ln P2 by P1 plus MCV ln V2 by P1 plus MR ln V2 by V1. Okay. Next, you see what are the common terms are there. You see ratio V2 by V1 is there in the second term, and V2 by V1 is there in the third term. Okay. So you don't change the first term. You put as it is MCV ln P2 by P1 plus you take m common, cv plus r ln v2 by v1. Okay, so m cv ln v2 by v1 plus m into cv plus r ln v2 by v1. Okay, next you write the first term as it is mcv ln p2 by p1, and cv plus r, as I said, it is nothing but your cp, because r equals to cp minus cv, so cp equals to cv plus r. You replace the term cv plus r with cp, so mcp into ln v2 by v1. So final equation is S2 minus S1 is mCV ln P2 by P1 plus mCP into ln of V2 by V1. So this is the expression for entropy change in terms of pressure and volume, and this one is entropy change in terms of temperature and pressure, and first one is the entropy change in terms of temperature and volume. Okay, so in the exam they'll ask derive the expression for entropy change for any process in terms of t and v, means you have to find out this one. Second one, in terms of t and p, you have to derive this expression. Okay, and in terms of volume, we have to derive this expression. Okay, these are the three standard derivation for entropy change for any process. Understood these derivation? Any doubts? Okay. Any doubts? Do you have any doubts in this derivation?
No, sir.
Okay. So first you understand the concept of entropy, the formula of entropy, that is, you remember ds equals to dq by t. So whatever equation is there, you have to remember this one, ds equals to dq by t, for deriving the things. Okay. And now I'll derive the most important. Okay. The entropy change for the various thermodynamic process, how we derived the expression for work done during various process, like that. In this chapter, we are going to find out the entropy change for various thermodynamic process. Okay, you see the change of entropy for different process. Okay, first one. Okay, first you should know nature of core, you remember. Okay, so in PV diagram, the constant volume process is represented by the variation like this. Okay, so it is 1 to 2. Okay, oh, sorry, this is a misprint. Okay, you take this as a 1 and this as a 1 and 2. Okay. This is the nature of curve for the entropy change. Suppose you take temperature as here T1 and temperature T2. S1 is the entropy and S2 is the entropy at state point 2. Okay, nature of curve for constant volume is like this. Okay, in the exam they may ask, write the TS diagram for constant volume process, means so you have to write the nature of curve like this. And in PV diagram, we are going to represent vertical straight line for constant volume process. The another name for constant volume process is isochoric process, and this is the nature of curve. Okay, okay. And this is the expression for the heat transfer during the constant volume process. You remember this formula, Q equals to mCV into delta T. This is the amount of heat transfer during constant volume process or isochoric process, where M is mass of the working substance in kg, Cv is specific heat at constant volume, and delta T is difference in temperature, that is final temperature minus initial temperature. Okay, this is the standard formula for the heat supply during constant volume process. So whenever you apply for differential format, okay, we are going to write in the differential format like this: dq equals to mcv into dt. This is the differential form of the above equation. Now we are going to divide throughout by temperature T. That is dq by T equals to mcv into dt by T. Okay. So as I said, dq by T is nothing but the entropy change ds equals to, just you replace dq by ds equals to mcv into dt divided by T. In order to find out the total entropy change between the states 1 and 2, we are going to integrate this equation between the state points 1 and 2. Okay. So, starting always you have to write this equation. Next, you are going to uh, write in differential form and then divide throughout by t. Next, you have to replace the term and then integrate. These are the four steps you have to remember. Okay, integration on both sides. Integration of ds equals to mcv is a constant term you take outside. Integration of dt by t between the limits e1 to t2. So s2 minus s1, as I said, integration of ds is a definite integral. S2 minus S1 equals to mCv into integration of dt by t is ln t2 by t1. So this is the expression for the entropy change during constant volume process. Okay. Can you tell what is the work done during constant volume process? What is the work done during constant volume process?
Zero, sir.
Anybody?
Zero.
Zero. Okay, like that you have to remember. Zero is always zero, and delta we studied. So these three, first we are going to study work done. Next we studied change in internal energy. That is q equals to delta u plus w. Okay. So anyhow w is zero in constant volume process. You have to write q is delta u. And third part is change in entropy. Change in entropy is given by mcv into ln t2 by t1. Cv is specific heat at constant volume. Specific heat at constant volume is defined as the amount of heat required to raise unit mass of the substance through unit degree rise in temperature at constant volume. That is the definition of specific heat at constant volume. So you remember S2 minus S1, and you remember the nature of curve, most important. Like this, you'll get the nature of curve. Okay, as the temperature vary, the entropy also vary. As I said, the entropy depends upon the temperature. Okay, it's the first process. Then second process, how to write the TS diagram for constant pressure process. Second process is constant pressure process. The another name for constant pressure process is your isobaric process, you remember. Okay, and another name for constant volume is isochloric, and another name for constant pressure is isobaric process. You see, you'll get the same nature of curve. How we are having the constant volume, same nature. Okay, we in work done, the nature of PV curve for isothermal, adiabatic, and polytropic remains same. You know, like that in ES diagram also, the nature of curve for constant volume and constant pressure is same. Nature of curve is same. Okay, there is no change in nature of curve for constant volume and constant pressure. Okay, because this temperature is depends upon the pressure. That's why it varies according to the pressure. Okay, so nature of curve remains same. You have to draw the same diagram. Okay, then how you are going to write the expression for change in entropy? Okay, same process. Okay, you can take, instead of CV, you have to take CP. This is the amount of heat transfer during the isobaric process or constant pressure process. So Q equals to mCV. So in this case, you have to take Q equals to mCP. Instead of CV, you have to take CP. Then next step, you are going to write differential next divide throughout by the throughout and MCP into dT by T. Now, next step is you have to integrate of ds between the state points S1 and S2 is equals to you have to take C. Okay. So integration of ds is nothing but S2 minus S1 equals to MCP into ln T2 by T1. Okay. So in constant volume process, we are getting it as MCV ln T2 by T1. And in case of constant pressure process, we are getting it as MCP ln T2 by T1. This is the second process. That is constant pressure process. Okay. Next, isothermal process. Okay. So how we are getting the nature of curve in isothermal process? It is a parabolic curve. Okay, in PV diagram. So in case of TS diagram, isothermal process means what? Temperature remains same, no change in temperature. That is why we are going to represent it as the horizontal straight line because T is our y coordinate. Temperature remains constant means you are going to represent it as the horizontal straight line. This is the nature of curve for isothermal or constant temperature process. Okay, you remember, so you practice PV diagram for various process and TS diagram for all these 5 process. Okay, so third process is isothermal. The nature of curve is horizontal straight line. Okay, next we are going to derive the expression for the entropy change during the isothermal process. So as I said, first always you have to write Q equals to delta U plus delta W. Okay, so delta Q is you have to, this is nothing but your first law of thermodynamics. It is a differential form of first law of thermodynamics. dq equals to du plus dw. Okay, remember as I said, delta U is 0 in case of isothermal process. Okay, delta U is, that is, there is no change in internal energy in case of isothermal process. Okay, because the internal energy is function of temperature only, T1 and T2. So in isothermal process it is same, since du is 0. Okay, so as I said, you have to remember the standard formula for internal energy is nothing but mcv into delta t. There is a standard formula for delta U, whatever process it is. So du is 0 in case of isothermal process. You remember du equals to mcv dt, standard formula. Like that we are having dh equals to mcp dt. These two things you should keep in mind. du is always mcv dt and delta t is 0 in case of isothermal. Directly you take dq equals to dw. Now dw is nothing but p into dv. Okay, so this is the p dv or displacement curve. dq equals to p into dv. Now once again same process you follow, dividing throughout by t. dq by t equals to p by t into dv. Now dq by t is nothing but ds. Okay, and p by t, as I said, pv equals to mrt. Okay, you apply standard ideal gas equation. So p by t equals to mr divided by v. Okay, p by t is nothing but mr by v. They replace the term p by t as mr by v in the next step. Okay, now next step is integrate between the limits 1 and 2. That is S1 to S2 equals to mr integration of dv by v. Okay. So integration of ds is nothing but S2 minus S1 mr constant term ln integration of 1 by v dv is nothing but ln of v2 by v1. So this is the expression for the adiabatic process. Whatever first I derived, those are general equation. Now I am doing the derivation of entropy change for individual process. The third process, S2 minus S1 is mr ln v2 by v1. Okay. Next, adiabatic process. So adiabatic process is nothing but the process in which there is no heat transfer at all. Okay, so this is the nature of curve. You remember how we are going to represent constant temperature process is represented by horizontal straight line, and here adiabatic process is represented by the vertical straight line. How we are getting the vertical straight line? Okay, so we know that ds is dq by t. Okay, you apply the standard formula. dq is 0, means there is no heat transfer for adiabatic process. ds is 0. Okay, whenever ds is 0, integration of ds equals to integration of 0, means we'll get the s as constant. Okay, okay, this one more step it is missed here. Integration of ds equals to integration of 0. Integration of ds is nothing but what? S2 minus s1, and integration of 0 is nothing but constant value. So ds is nothing but the constant line, that is vertical straight line in case of adiabatic process. Okay, for isothermal process, you are going to represent it as the horizontal straight line, and for adiabatic process, you are going to represent TS diagram as the vertical straight line. Okay, how you are getting vertical straight line? So you have to apply first law of thermodynamics. There is no heat transfer, and just you take the ratio ds equals to dq by t and integrate both sides. Integration of ds is integration of 0. That is nothing but s2 minus s1 is constant. Always you have to entropy remains same in case of adiabatic process. There is no change in entropy. Hope you understood all the derivation, and in tomorrow class I'll derive one more derivation, that is the entropy change during polytropic process. Okay, these are the most important derivation. Okay, so go through all the derivations properly, and in tomorrow class I'll derive the expression for entropy change during polytropic process. Okay, so meantime, so all of you have to take sheet and then draw the PV diagram and TS diagram for all the 5 process. The nature of curve differ. Okay, uh, you'll get constant vertical line in case of adiabatic process, the constant horizontal line in case of isothermal process, and there is a variation line in case of constant pressure and constant. Guys, please give your attendance. I'll call one by one. Okay. Number 1, Abhishek Joshi. Number 1. Number 2. Number 3.
Present, sir.
Number 4. Number 3 present.
Yes, sir. So 3 and 4 both present.
3, yeah? Okay.
So 3 and 4.
3 and 4, okay, okay. 5, Ayush Chandra.
Present, sir.
Okay, okay. 6, Lalit.
Present, sir.
Okay. 7,
Present, sir.
8, Banashankar TJ.
Present, sir.
Okay. Bhavana Devi.
Present, sir.
Brijesh MR, number 10.
Yes, sir.
11, Chetan Kumar Ji.
Yes, sir. Yes, sir. Yes, sir.
Okay. Chinmay Shetty, number 12. Chinmay Shetty. Number 13, Chirant. 14, Darshan. Darshan R.
Yes, sir. Present, sir. Present, sir.
Okay, okay. Dorje, number 15. Number 16, Harshit Kumar. 16. Harshit Kumar is not there. 17, Harshayappa. Harshayappa. 18 Shashank, 19 Yatindra, 20 Karthik DB.
Yes, sir.
Karthik understood all the things. Any doubts?
No, sir.
Do you have any doubts?
No, sir.
Okay. Karthik N, number 21. Karthik, sorry, Kritik N. Kritik. 22 Madhu P. 22 Madhu. 23. 25 Mohsin Shaukat. 26 Naman. 27 Shrikant P.
So Naman is
P.
present, sir.
Naman is present.
Yes, sir. He is texting to tell his mic not responding, I guess.
Okay. I give attendance. Okay. Shrikant P. P. Shrikant. Number
26 present,
27.
sir. Sir,
Okay.
26.
I give attendance. 26 present. Okay. Naman. Okay. 27 P. Shrikant is there. Shrikant. So all of you have to attend the class. This is thermodynamics subject. Other subject by reading you can understand, but thermodynamics is not like that. You have to attend all the classes, understand the concept. Okay. So meantime, you have to refer standard textbooks. Shrikant absent. Okay. 28 Pawan Naik. 29 Parth Sarthi.
Present, sir.
Okay. 31 Rahul Rathod. Rahul Rathod.
Present, sir. He was.
Sir, 17 present. My mic was not working.
No. 31 Rahul Rathod.
No, sir, 17.
17. 17 Harshayappa.
Yes, sir.
Harshayappa. Okay. Give the attendance. So you please tell your problems. No problem. I'll give the attendance.
Sir, also
but you
21,
tell your
sir.
USN.
Hello,
Sir.
sir.
Which one?
Sir,
21,
21.
Yes, sir.
21 Kritik.
Sir,
Yes, sir.
25.
21 present.
Sir,
Yes, sir.
55.
25.
55, sir.
55. No. No. Rahul Rathod. Okay. Next Rajat Patel.
Okay. No.
Rajat Patel. 32. 33 Rennie CB. 34 Rohan. 35 Shreyas. 35 Shreyas. 36 37 Samarth Nadik. 37 38
Present, sir.
Sam Gore.
Present, sir.
37 Samarth Nadik absent. 38%. 39 Banerjee is there. 40 Shashank. Okay. 41 Shashank. Okay. Shashank MV. 41.
Sir, 40
42
present, sir.
Shivkumar. Shashank is present. Shashank MV 41. 42 Shivkumar Patil. 43 Sriharsha. 44 Shubhankit Singh. 45 Somesh Kumar present.
Present, sir. Present, sir. 45.
Okay. 46 Spurti Devi. Spurti.
Present, sir.
47 Dev
Present,
Charan.
sir.
Okay.
Is absent.
Absent, Dev Charan.
Tanvir Hussain, number 48. Tarun M, 49.
Present, sir.
50 Tarun Gowda.
Yes, sir.
Tarun Gowda. Okay.
Present.
51 Vasant Kumar Ji. 52 Vinod Kumar S.
Present, sir.
53 Vinukonda. 54 Vivekananda. 55 Gaurav Srivatsav.
Yes, sir.
18 series Nitin. Shibam Barkotoki. Shibam. And Manu Hariharan.
Present, sir.
Manu Hariharan, na?
Yes, sir.
Hello,
Okay.
hello.
Shibam Barkotoki.
Yes, sir, present.
Hello, tell me. Okay. Okay. Any name left out?
Sir, 31 Rahul Rathod, he had network issue.
31, na?
Yes, sir.
Rahul Rathod.
Sir, he had network.
Yes, sir.
Yes, sir.
Rahul Rathod present. Okay.
Okay.
Anybody? Okay. Thank you. We'll meet tomorrow. Okay. Don't miss the class. You attend all the classes regularly. Thank you.